So now 10.6, 10.7, part 2. We're going to finish the packet, and we're dealing with continuous mass distribution. So before we were looking at having kind of like blobs of points all over the place, but a solid object is just made up of mass that's distributed over a whole area. And so when we have that, instead of adding individual components, we have to add up a whole bunch of things like a whole area. And for that, we use the antiderivative. We integrate. And so you can see the derivation for the moment of inertia around the center of mass for a thin uniform rod. So imagine we have just a rod, a thin uniform rod. If we go about the center, what is the moment of inertia for that? And you can tell it's the same process, very, very similar to the process that we used when we were finding the center of mass if we had a changing linear mass distribution. And you can see that this was on a recent test. This type of question does show up on the AP exam, where they ask you to derive the moment of inertia about some axis on a on some object, like a thin uniform rod. And so 1/12 ml squared. That's something that you need to know. Memorize that one. You're going to have a quiz. It's an I quiz, and in the I quiz, you have to memorize these. This is one of those. Okay. For a thin hoop, that one's pretty easy because there we are adding up, but all of those pieces of mass, they're all the same distance from the radius. And so there's really not a lot to add up. We're just adding up all of the pieces of mass, but the mass is all the same. It's not changing with respect to the radius. And so when we integrate, we simply get mr squared. So if I have a thin uniform hoop, then it's mr squared. Same thing for a cylindrical shell. A cylindrical shell is just like a lot of thin hoops stacked one on top of the other. And so that one also, the moment of inertia about the center of mass is mr squared. Adding up for a disk, though, is a little bit different. And what we've done here is we've taken one of those circles, like we kind of split it up into thin hoops. And we take those and we take the hoops and we stretch them out so it's like a rod, so we can think about what's the area of that thing. And then we look at things in terms of sigma, an area, the area mass density instead of the linear mass density. We see how that is changing, right? The amount of matter that's there in each hoop depends on how far it is from the axis. And when you go through the operation, you can follow step by step, and we get that the moment of inertia is 1/2 mr squared. That one also you need to know, and it's the same as a cylinder, because a cylinder, again, is like having one disk stacked on top of the other, and that would be 1/2 mr squared. Okay, for a uniform solid sphere, this is kind of like having disks of changing size stacked on top of the other. And so that's the procedure here. We're looking at rho, so we're looking at volume mass density here. And that's necessary for finding, for doing the derivation. And you can follow the steps. You're not going to need to know how to do this, but it might help you conceptually to kind of look through and see how this all works. In the end, what you need to know is that the moment of inertia is 2/5 mr squared. Memorize that one. Okay. And don't mix it up with a hollow sphere, which we don't have here, but it does show up at the end in that last page from page 253 of the text. The last page, you need to fill that in. It's 2/3 mr squared, and those are the ones you need to memorize. And if you think about it, it makes sense that for a solid sphere, you have mass concentrated in the middle. The more the mass is concentrated in the middle, the lower the moment of inertia. Right? But if you have something where the middle is taken out and you have just the spherical shell, then you have more mass distributed around the outside, a larger moment of inertia. 2/3 mr squared is larger than 2/5 mr squared. Right. So the way you can kind of remember it is that they're both 2 something, right? 2/5, 2/3, the sphere and the shell. but the solid sphere is less, so that's 2/5 mr squared. Right, and then don't forget the parallel axis theorem and the plane figure theorem, and you're going to see now how these are used in a couple of problems. In example 1, we can use the parallel axis theorem to find the moment of inertia. So we're given this rod. Here's the center of mass, and here's axis QQ, and axis PP. So this axis is the one that we'll use to find, through one end of the rod, because that's through one end of the rod. So we have 1/12 ml squared. That's the moment of inertia just of the rod through the center of mass. And then we're going to add m, and then the distance 1/2 L squared. Because IPP should be I, the center of mass, plus mh squared. H is the distance from the center of mass to this axis, and that's just that. And so what we get here is, this is 1/12 ml squared plus 1/4 ml squared. Simplify that, and we get 1/3 ml squared. This is one that you'll have to memorize. Or you don't have to memorize it, you can just know the formula. But that's one you're going to want to know very quickly. Okay, and then through a point 1/3 of the way from one end of the rod, we'll say that that's Q, that that's 1/3 of the way from the edge. So this is question B. And again, we're going to use the parallel axis theorem. This is going to be QQ is 1/2 or 1/12 ml squared plus mh squared, and then that distance is not from the center of mass to here, is 1/6 of L. 1/6 L squared. Again, we simplify down, and we get 1/36 ml squared. So that's going to be 1/9 ml squared. That one you don't have to know, but this one you should know offhand. Example 2. So now we have a cylinder. We're finding the moment of inertia around this axis, PP, which is on the side. And again, we're going to use the parallel axis theorem. So IPP is going to be I, the center of mass, plus mh squared. H is the distance from here to here. So this is 1/2 mr squared plus, and then m, h is just r, so that's r squared. So we get 3/2 mr squared. Example 3. We have a uniform disk, as shown. Find the moment of inertia of the disk about PP, which lies in the plane of the disk. So right here's line P. We can make another axis perpendicular to this. We'll call it LL. So now I have 3 axes, which are really like the X, Y, and Z axes, right? X, Y, and then Z is coming out. And so according to the plane figure theorem, I about the center of mass, like what we normally have, is IPP plus ILL. But because these are symmetric, L and P, these are the same. Right? IPP is equal to ILL. So I about the center of mass is 2 IPP. And so this is 1/2 mr squared equals 2 IPP. So then the moment of inertia around this axis, PP, is simply 1/4 mr squared. And again, this we This is the plane figure theorem that we use to solve that problem. Okay, in example 4, we have a circular hole in a large disk. Find the rotational inertia of the disk about an axis normal to the disk and through the center of the solid. So here it is. Looks like this. And we'll call this R. And this is R over 4. And from here to here is R over 2. Okay. And so we're going to do I total, the whole disk. The disk without the hole would be I center of mass equals 1/2 mr squared. Right. That's through this axis, right, perpendicular to the surface and through the center. So now what I'm going to do is I'm going to find the moment of inertia of just this hole, about this axis, and then I'm going to subtract that from this. Okay. So this is the mass of the whole thing. Well, first I need to find the center, the moment of inertia of this hole. So I need two things, the radius and the mass. So the mass of the hole is going to be, I know that the mass of the whole thing is I can set this up as a ratio. The mass and then the mass of the whole is pi r over 4 squared, and then the whole mass is like pi r squared. And so this ends up being, the r's cancel out, the pi's cancel out, I get 1/16 of the total mass. So that's the mass of the hole. And now the moment of inertia of the hole is going to be 1/2 the mass of the hole times the radius, so r over 4 squared. And this comes out to, let's see, 1 over 512. Okay, so using the parallel axis theorem then, this is 1 over 512 mr squared plus, again, 1/16 of the mass, and the radius, it's half the radius because it's half the radius from there, squared. And we simplify this and we get 9 over 512 mr squared. So now we have I total is going to be the moment of inertia of the solid minus that of the hole. And so I have 1/2 mr squared minus 9 over 512 mr squared. Okay, so 1/2, this is 256 over 512 mr squared minus 9 over 512 mr squared. And so we end up with 247 over 512 mr squared. And that's what we expect. It's a little bit less than half. Since I take out part of this, I have less inertia, less mass that I'm having to accelerate. And so I expect the moment of inertia to go down just a bit, and I get something that's just a little bit less than 1/2. Okay, and here on this last page, that thing, you can fill that in. You can go to the textbook or you can use what we've got here. And the only two on here that you don't need to memorize, or rather the only three, are like the one in the middle on the left, the cylinder about a central diameter, and then the bottom two on the right. These two you don't need to know. But the rest of these you do. The ring, the cylindrical shell, the cylinder, um, the thin rod, the hollow shell of the sphere, and the solid sphere.